Good morning, everyone. So today we have the second part, so the part B of bifurcations in the phase plane. So maybe you have realized already, but we have talked about bifurcations, yes, but that account only for real eigenvalues. In terms of like you have two eigenvalues, okay, let's assume two are negative, then one become positive, and then we go from a tractor, let's say, to a saddle. So in that moment you realize that one eigenvalue has to go through zeros. So you have from negative, zero, positive, or the other way around. And this is the sort of bifurcations that summarizes in the saddle node, transcritical, or pitchfork bifurcations that we saw. Okay, and this somehow had already like counterparts in one-dimensional systems. But now we will talk about another kind of bifurcation that does not exist in one-dimensional systems, and this is when you have actually complex numbers. Okay, and this is the case of the Hopf bifurcations. So in this at this fixed point, so the fixed point loses stability without colliding without any other fixed points. So if you remember, this is the our formula that has been with us already for a long time, and we know that this can lead to a complex number if this quantity here is smaller than 0, and we will obtain a pair of conjugate eigenvalues. Let's say there are complex conjugate because of this plus and minus. So this is the case. Now we're talking the complex plane. This is the case that we have already seen where both eigenvalues are real. Okay, so in here there is no value in the imaginary axis, and we see that when we have bifurcations, it means that one of these two eigenvalues crosses the zero line and becomes, for example in this case, positive, or it could be the other way around. Okay, so this is the case of the saddle node, transcritical, and pitchfork bifurcations. But now if we go to the other case, when we have this complex conjugate eigenvalues, we will have this situation. They will have the same real part, and they just differ in the sign of the imaginary part. The distance to the real axis in here is the same. Now let's assume we have a parameter, okay, mu, that when it changes, then the two eigenvalues will actually move, and they will cross this imaginary axis at the same time. And in that moment, we say that a Hopf bifurcations has occurred. And similar to, for example, the pitchfork bifurcation we have already seen, we can have supercritical and subcritical bifurcations. It can be easily shown. So let's assume we have this system. So we have a linear part, and then we have these nonlinear terms. If you just use the quadratic formula, you realize that these are the actual eigenvalues from these metrics, and this is gonna be the oscillatory part, okay, and this is the damping term. Remember that we can use the Euler formula, so we have exponential lambda, which is exponential mu exponential e omega, and there we have just okay, and in analysis the answer actually only considers the real part most of the time. So this is the oscillation and this is the damping term. So just remember that mu has to be negative so that an oscillation decays, or positive so that an oscillation just grows in amplitude. Let's have this example. Imagine you are given these like snapshots for different values of mu, like this. This is just an example, okay? So we have the time signal, so the signal depending on time, and also we can have this in the phase portrait. So here we have an ellipse, a spiral that is just oscillating, so like circling the origin until going to the origin. Here we have just a perfect circle, and here we have just the same and a spiral, but just that goes away from the origin. So if I just ask you, what is the moment where the bifurcation occur, what would you say? Okay, and the bifurcation actually happens when the spiral that was actually going to the origin changes and start getting away from the origin. This is for different values of mu, okay? So remember, this is a parameterized already equation. So yeah, I think most of you have thought the same thing. This is the point with the Hopf bifurcation occurs. What we just saw here is a supercritical bifurcation. We can just, for example, write this down in this little axis. Imagine here, this is mu 0, and this is the amplitude of the oscillation. So we see that at every point the amplitude is going to be 0, because we wait until the oscillation decays, or until the steady state, and the steady state in this case for negative mu is that there is no oscillation, so we just have nothing. In this moment we have the corresponding mu equal to 0, and there we will have start to have the oscillations, okay? Of course we will need higher order terms in order to have a oscillation that goes into a limit cycle, okay? But what I want to show you is this path in here, okay? So right now we are not talking about just a given value. Before it was just x, but now we are talking about in this axis about the amplitude of the oscillation when the corresponding steady state is reached. We can have also the case of subcritical bifurcations. So remember, these are the dangerous bifurcations, because in this case something that was exponentially decaying, is assume these oscillations going towards amplitude 0 suddenly become of very high amplitude. In this example we use just polar coordinates, so r is going to be the amplitude of the oscillation, and then we have these two equations, and just by solving you could realize these two situations. One, we have an oscillation, so this is going to be like this limit cycle that is unstable. Therefore any oscillation, any perturbation around this line will lead to a decay towards the origin, or it will grow until reaching another limit cycle. In here, just by changing a given parameter of mu, you just have that the origin is unstable, and this somehow spirals until reaching a limit cycle at a very large amplitude. Sometimes these kind of scenarios are much more well understood if we just draw the bifurcation plot, okay? So from this we can actually already somehow design or have the big picture. We know that we have mu 0, and this is, let's say, yeah, mu 0. So for mu larger than 0, then we will have a limit cycle here that is very large in amplitude. So let's just put one point in here, so this is large in amplitude. For mu less than 0, so somewhere in here, let's assume, we have a B-stable condition. B-stable because we have 2 points that are possible that assure a stable situation. So we have the origin and also this limit cycle that is of a smaller magnitude than this one. Okay, so we have something like this. Then we have a limit cycle that is unstable, so just unstable, and then we have the origin that is stable. So with this information, we can already somehow see the big picture. So we can say that the origin changes stability after the half bifurcation. Okay, so this is stable and then this is unstable. Then we have here this limit cycle that is unstable, and this point is joined with the half bifurcation, which is in this is the half bifurcation. And then we have a stable limit cycle. Okay, let me just put this arrow with black so not confused. So you can see already that this is a dangerous situation. We have a subcritical bifurcation. Okay, and this looks exactly the same as before, but now the only difference is that we are talking about the amplitudes of the oscillation. Okay, and all these oscillations, most of the time they are related, or they are just actually limit cycles. Okay, this is something you already know. So 1, 2, 3, answer. Yeah, I assume most of you, or actually all of you, answered correctly. This is an interesting picture about an experiment that was tracking the pressure amplitude in the oscillations. So we have here the inlet air is coming from here, then there is the flame holder, and there is the flame here, and there are all the combustion chamber with the hot gases are in here. Okay, so this somehow resembles the combustion chamber of an engine, of a gas turbine. Now if everything is nice, is operating correctly, this flame actually is just oscillating as the turbulence is actually happening. It means that you have like a sort of white noise, if you want. Okay, so there is not really like a preferential frequency of oscillation. Therefore everything is fine, and these oscillations are actually small in amplitude. This is a desired operation. Under some circumstances that are not simple to identify, you may have strong oscillations at a given preferential frequency, and the flame actually can go backwards and forward, like oscillating in this direction, and you can create like huge vibrations in the whole engine, or in this case in the whole combustion chamber, but in the gas turbine itself can be the whole engine vibrating, and this is pretty dangerous. Okay, so you know, I mean, the best would be to have a model that is able to retrieve this kind of behavior. So until where can I, for example, inject fuel and still avoid this sort of oscillations? Sometimes this model is actually is just doesn't exist. So what you can do is just to do a parametrical analysis in an experiment. And this is what happens in this study of MOEC 2008. So there are given preheat temperature, and they consider a given equivalence ratio, so a given amount of fuel in the engine, and they realize this kind of behavior. They see that they can preheat the temperature until 70 degrees, but if they go beyond that, then this is the preheater, then you will start having strong oscillations. Okay, so in here these oscillations are related to turbulence. In here is just the acoustics of the combustion chamber that are huge. Now if they want to make it go back to the stable operation, you realize that the oscillation just not go backwards in here. They have to have the preheater going on until 30 degrees, and then they will find the original state, which was the desired one, the stable one. So you see here two different paths, and then you realize that this case is exhibiting hysteresis. You can do the same experiment, but instead of changing the preheat temperature, so this is your parameter. Now your parameter is going to be the air mass flow, and you can still have the same hysteresis. Okay, now you change another parameter, so that you just consider another amount of fuel. So instead of having a very lean combustion, you can just enrich it a bit, so add more fuel per kilogram of air, and then you do the same experiment that in here, but then you realize that the path going forward is the same going backwards. Okay, so from these two plots you can already identify that the bifurcation has changed in nature. Here we had a subcritical bifurcations, here we have a supercritical bifurcations. Okay, so this is something that can be done when you want to know or to learn something about your system, to do a parametric variation and see how your system reacts, and then based on how it reacts you can somehow put it in some boxes in terms of, okay, this is a system that is pretty dangerous, this is a system that can be handled, or something like that. Okay, this is just what I draw before. So this is the supercritical, this is the subcritical, this is the Hof point. Okay, and when you have this subcritical bifurcation, you can find also this fault point. So these 2 points are, so these are then their names. Well, the idea is, okay, you may have the experiment, then you just do the parametrical variation and identify if you have hysteresis or not, and then you want to model it. So how you do modeling? So you could do weakly nonlinear analysis. So this is by using, for example, perturbation theory, when you identify what is happening very close to this Hof point. Okay, you just analyze if you have some, how many, you have a limit cycle close to it or not, something like that. You can use frequency analysis. I will just talk about this in the last lecture when I present what we do here in thermoacoustics for when considering limit cycles and in corresponding analysis. And also you can use continuation analysis. Basically this is just to track every single limit cycle. So imagine you just have your system of equations that are nonlinear, then you just solve them and identify a limit cycle, then you just change the parameter a little bit and identify the other limit cycle. So you do like a continuation method and you just track the whole bifurcation plot. So we have already talked about oscillations and Hof bifurcations. We will change the topic. Okay, Now we will talk about coupled oscillators and what is quasi-periodicity. So this is very interesting because you can consider a system that is a complex system to be like a combination of oscillators. So one oscillator can work in a given specific way, oscillate at a given frequency with a given amplitude, and then you just put it together with another oscillator, and the system itself is completely influenced by this new oscillator. So we can have cases of synchronization, for example, and this called that and this feature that is called quasi-periodicity. And now we go again and use polar coordinates. So it means that we have just here the information of the angle, and the angle of one oscillator defines it, the angle of the second oscillator defines it, and here we have a function of the two angles. Just to be, just to know we're talking about the same thing. Polar coordinates mean that we have, this is gonna be x, y, but we prefer to use r in vez of the coordinates x, y. We use r, theta. Okay. So the change of the angle in time here is nothing but the angular frequency of the oscillator. And this is perhaps one of the most basic models for coupling oscillators, but also one of the most used. So this is a very nice thing. So imagine the function here is simply given by a given constant, which is gonna be called like the strength of the coupling, and then this argument in the inside a sinus function. What does it mean? That there can be two situations where these functions are not there or are zero. One, when this angle is, so when this distance is large enough, this is something we will see just in some slides, or when the coupling strength is just zero. So in that sense, you can realize that when this is zero, these two oscillators are completely uncommunicated. So they just do whatever they do without telling the other. So this is why we can talk, for example, under this model, that the frequency of oscillation of theta 1 is going to be omega 1, and here of the theta 2 is going to be omega 2. They will oscillate at their own frequencies and don't care about the other one. So even that case, which is very simple, already presents some interesting features. If you think this in a more physical way, then you can just associate that a given oscillator has its own natural frequency, and these omega 1, omega 2 are referring to the natural frequencies. We can have an intuitive example. This is also from the book of Strogatz, which is pretty interesting. Imagine you have, this is gonna be a circuit, and these two guys that are running, that are doing some sports, and this girl is pretty fit, so she's just completing circuits pretty fast. So the angular frequency here is actually pretty fast. And this guy here is a friend of hers, but is not as in a good shape. So actually he's completing the same circuit at a very low frequency omega 2. Okay, so basically at a given instant, if they start at the same time and at the same position, you will see that the angle, so the distance between the girl and this guy, is going to increase with time. Okay, so there are two possibilities. Imagine that she really needs to run at her own pace, so they say, okay, whatever, I cannot wait for him, so they just run completely uncoupled. So you can say that these two guys are completely non-synchronized, and she will just run at his angular frequency, her angular frequency, and he will run at his angular frequency. Now let's assume that there is something called coupling strength, which means that there is a very strong friendship. Okay, Friendship intense and she is not worried about running slowly, so she will just wait for him, and the guy will accelerate a bit so that she doesn't have to do the whole sacrifice, let's say. So at the end they will find a compromise, and they will find an angular frequency that is between omega 1 and omega 2. In that moment, these two guys will run at the same frequency and they will be synchronized, okay? But it depends on the coupling strength. If the coupling strength is not enough, she will just care about herself and about maintaining her own pace. This is one thing. The other thing is also the distance. Imagine they are okay, they are almost good friends, so but the coupling strength is not big enough. However, this guy is in very good shape, and therefore maybe theta 1 and theta 2 or these angular frequencies are also very close. So she will say, okay, let's just do this little sacrifice. I just slow down a bit to wait for him, okay? So if these phases, so the distance, are not large enough, there is also a very easy possibility for synchronization. So you see we have these angles, theta 1 and theta 2, and it can be drawn in different, let's say, frames. So we have the polar coordinates. This is something we just saw with the example. We can also have torus coordinates. So basically it's like a three-dimensional plot. So one angle is rotating here, and while this rotates. So you can just portray this in a toroid. And also there is this very highly used frame of drawing, which is the square with periodic boundary conditions, okay? So you maintain theta 1 and theta 2. This is something I will just explain in the next slide. Okay, so let's consider this case when the coupling is not there, and therefore we have this situation. So what the situation is, what is of interest, let's see. So we will learn how to draw this in this square box. So let's assume we have these two oscillators, and we have already a relation between frequency 1 and frequency 2. So here you realize that frequency 1 is larger than frequency 2, okay? So when omega 2 is equal to 1, omega 1 is equal to 2. What does it mean? So this box and this box, one of those is incorrect. So we have to find out which one is the correct one. So let me just describe them. While theta 1 moves, it has moved 1, so it has completed one circuit. Theta 2 has completed half. When theta 1 has completed 2 times, so I have displaced 2 times in here, 2 times theta 1, theta 2 has completed 1, okay? And this is actually this is what this equation is saying. When omega 2 is 1, omega 1 is 2. So just put pause if you want, and just try to find out if this or this one correspond to this one. As you may already realize, this is the correct one, because theta 2 moves 1 while theta 1 moves 2. So this is the correct square representation. Okay, so let's do it in a more, let's say, complex way or difficult way. So now we will have this relation. While theta 2 completes 2 circuits, theta 1 complete 3 circuits. Okay, again put pause and think. Then again, this is the square that is winning. So you can see that in this case the oscillator completes 3 circuits while this one completes 2. And if you go in here, you say this is 1 time, then 2 times, and then 3 times. And in the same way, so in theta 1 was 3 times, and theta 2 is 1, no, 1, 2. So that's why this one is the good representation. This one will be the other way around. This one will be 2 over 3. Okay? And just maybe I haven't said that explicitly, but maybe you already got it. These are periodic boundaries. So if I go from here, I enter from here. If I go from here, I enter from here. Okay? So this is the idea of this square representation. So in the same way we use the square representation, we can also use a toroid. So this is a three-dimensional donut if you want. And then you see this is the theta 2. And theta 1 is, imagine you start from here, you go out and then you go behind and you go up. So this is already 1. And you realize that you start from here, you do 1, and you have done 2/3 around the torus. So basically, if you do this 1, then you do 2, you do 3, you have done 3 revolutions, and you have already turned twice. Well, this is a little bit more complicated. I would say for me it's much easier to understand this square, but it becomes actually very useful, we will see, when we are talking about quasi-periodic oscillations. Why? So let me just go to the next slide. So far we have these 2 examples where P and Q are rational. So these are periodic oscillations. But we can have also the situation where P and Q are, so that the ratio is irrational. In that case, you will realize something very important is that you will start, let's say, from here, and you do not ever close the circuit. So you will go around these periodic boundaries forever until you have a completely black square full of eventually infinite amount of lines. Okay, so this dense square is telling you that you may have quasi-periodic oscillations. When you represent this in the toroid, it is also helpful because you can clearly see. So I will show you 2 examples. In this slide, we see several cases, like several type of limit cycles, and this is the one I wanted to show you, the quasi-periodic oscillations. So you see here, there is not like a clear pattern, okay? Here, for example, in period 1, the pattern is clear, so every period you will have like this kind of sawtooth. In the period 2, you have these 2 bumps that repeat forever, so you will have a period 2 limit cycle. In the quasi-periodic, then there is no pattern, okay? And sometimes it's interesting to see that as a first glance, it can be confused with chaos or with aperiodic oscillations. But if we go to the next slide, we can see how you can represent this in the phase portrait and also in the so-called Poincaré map. Okay, so in the phase portrait is you have a three-dimensional, so you have 3 directions where you actually plot your orbit. Obtaining these 3 directions, if you have a 3-dimensional system, is not a big deal because you know that every dimension is clearly defined. However, most of the time you have to understand a very complex systems and reduce it through 3 principal dimensions where you will plot these kind of portraits. You have here, for example, the period 1, so you have just one orbit that is closed. Period 2, it does like a little turn, before joining again the orbit. So this is how you can characterize it. You can also cut it in this Poincaré map, and then you can see like the cross section is gonna be just 2 dots. In here you will have 4 dots. But what happens when we go to quasi-periodic oscillations? In this case, this is a toroid, and it is super black, it's full of lines. When you actually do the cross-section cut to obtaining this Poincaré map, you will see that these, let's say, sections are empty inside. So this is a perfect toroid. We will see that you can somehow at first glance confuse it with chaotic oscillations, but when you have this sort of cross-section figure, you can see that this clear pattern of quasi-periodic oscillation is not anymore present for the chaotic oscillations. Okay, but this is just to show you. So the idea of this slide is to show you how a toroid looks like when you have a quasi-periodic oscillation. So far we just considered that these two oscillations were not coupled. So this k was 0, for example. Now let's consider the complete equation, and let's analyze the case of synchronization. Okay, synchronization means that the phase between theta 1 and theta 2, so this like angle, if you want, is constant, doesn't change. How can we represent that? We just define this angle, so the phase, and we just want to know like the rate of change of this, and we just replace here these expressions. And now we say, let's investigate the case when this phase is constant, and we just find actually the fixed points. Okay, in this case then we obtain the expression for the fixed points, which in other words in this case is called synchronization. But there must be some conditions for that. So according to you, this fixed point is always defined, can always exist. So in other words, this quantity can be any quantity to obtain this fixed point. So just think, send me your ideas with the internet. Okay, I think one of you already got the answer. This quantity is bounded. Okay, it has to be between -1 and 1. If it's beyond that bound, this solution just doesn't exist. So what does it mean? So it just means that we need to have such a condition. And this is what synchronization is about. When this coupling coefficient is very small, you need then that the distance between, so the difference between the frequencies of the oscillations, the natural frequencies, is very small as well, so that we can have a frequency of compromise, or in other words, synchronization. When we allow these coupling coefficients to be larger, so it's possible to have synchronization even if the natural frequencies of each oscillator are far. So I just wanted to show you this little introduction, let's say, to synchronization. You will see that in nonlinear dynamic systems, you can have always the possibility of having an n amount of oscillators being coupled to express the complexity of a given system, the dynamics of a given system. So having the concept of coupled oscillators and synchronization is important. With the tools we already have, we can plot this like a one-dimensional phase portrait with the y-axis being phi dot, x-axis being phi, and we can see, we will observe that actually we have a saddle node bifurcation at this condition. You can actually plot this in Desmos if you want. This relation can have two solutions, one solution, or no solutions at all. And this is going to be just given by the values of omega and k you imposed. So the main idea, the main takeaway is to remember that when two systems are synchronized, we have a phase difference between them that is constant. So as you already expected, the angular velocity is the same for both oscillators. The technical jargon is saying they are locked on. So when two oscillators synchronize, they are locked on. And here we can demonstrate that the compromise frequency lies between omega 1 and omega 2. So you can get the oscillation frequency from this expression, so the angular frequency of any of the two oscillators, and then you just replace the value of sinus of phi star, and then you see that this is actually the final definition, or let's say evaluation of the compromise frequency, which is between omega 1 and omega 2. Now if we display this in the square as we did before, and we know that the difference, so the phase is constant, it means that if we just want to plot this in this square, we will have a slope equal to 1 all the time. So you can start with something different. You can have, for example, these thin lines making some turns like this, but eventually they will just converge to a line that is unique and is of a slope 1. Okay, so here this is the example. So let's talk a bit about Poincaré maps. So this is as just showing some slides before. If we have the phase portrait and there are these orbits, then we can just put a plane in there and just account for the intersections. In this case, you will see actually just dots. And then you can imagine you live only in the plane. So base given a value in xk, then you will have a transformation that will give you the point xk plus 1 and then xk plus 2 and something, maybe you just convert to a fixed point that doesn't move anymore. Okay, so this is a way of interpreting limit cycles as well, or orbits in the Poincaré map. So here the key, the important part is to understand what is this transformation, what is this Poincaré map. So here we can see, based on this possibility of these fixed points, you have a given argument and the final answer is the same. So it's basically you go and you arrive to the same point. So it's when you actually can identify closed trajectories, limit cycles, okay, for example. And something that is also interesting is that it's possible to identify if these limit cycles or these closed trajectories are stable or unstable. Again, we can just define this by giving a initial perturbation and see where the next turn, so the cross point is going to be. It's going to be closer or farther away. So this is the perturbation. This is the perturbation, and then we go back after one turn and see if this is going to be smaller than the initial one or not. In order to do this a little bit more formal, we can just linearize this exactly as we did it with the nonlinear functions f and g to obtain the Jacobian. So we can do the same thing here, and we have here this linearize p, okay? And of course, we should also remember there are higher order terms. From this, we can just simplify this, and we end up having just this transformation, okay? V0, V1. And the question is, how can we characterize this linearized Poincaré map to assure that we have something that is unstable, stable, or unstable? So basically, how to identify if perturbations grow or decay. So voila, is we need to compute the eigenvalues of the linearized Poincaré map. And you will see that these eigenvalues, well, you can note that with lambda, are called Floquet multipliers. So this is I consider a fancy name that actually correspond to the eigenvalues of the linearized Poincaré map. And now let's do this exercise. Limit cycles are stable if. So put pause to the video and just think what can be actually the answer. Well, I was a bit mean here. Actually, none of this is the answer, okay? The answer is this one. And I want you to differentiate between this condition and the condition we were talking about, a given fixed point being unstable or unstable, okay? And this is something maybe I have to just talk a bit, and we will do it in a generic way. So if we start with a ODE, you can write something like this: x dot equal a x. So this is a description of dynamics in the continuous time. Okay, here time is continuous. We can have also discrete time, and we can have something like this: e k plus 1. I will put another matrix because it's not the same. B. So this is if you want to make a discretization in time, so you can have something like this. And now how do you evaluate if you have a given perturbation? Imagine the delta x here. Now we consider a perturbation instead of a actual quantity. So let me just write it in like this: perturbation with a hat. And in here this is equal. So remember that every time you see this kind of ODEs, okay, you can see this as a growth rate. And you know also that for a ODE, you have this kind of solutions. So I will just write the eigenvalues of lambda, okay. So in this case, you can observe that the stability of the perturbation is just given by this lambda, in this case the eigenvalues of A, and they must be negative, so smaller than 0, so that this perturbation goes to 0 and means that the system is stable. In this case, this is a different story because we are now in discrete time, and then we just have a map between x and xk plus 1. So we just treat this matrix again in terms of eigenvalues, but now the eigenvalues are thought or are analyzed in a way. Let me just write this down. For example, let's just call bx or vv equal lambda v. So these are the eigenvectors of b, and these are the lambda of those associated with those eigenvectors. So this matrix can be actually represented by eigenvalues and eigenvectors, and the eigenvalues somehow can tell you how your system can dilate a given input, or how can it shrink it. And you can be safe that the input will not grow if the dilatation or given by the lambdas is not larger than 1. So if these lambdas are smaller than 1, you are safe that the dilatation is not going to ever happen. So the input is going to be shrinked all the time. Okay, so in this case, these Floquet multipliers, which is just the eigenvalues of this linearized Poincaré map, that's why they have to be smaller than 1, the absolute value. Okay, so we have arrived to the final part of this chapter of bifurcations. Next class we will talk about chaos. So I think you are waiting for that, so I think it's gonna be a nice one. Okay, so see you on Thursday. Bye bye.